Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I think, all sorts of questions here. Let me see. Well, there's a question here from Anne. How does sand form near the sea? Well, sand is crushed up rock, and it's formed by rock being crushed as a result of being pounded by ocean waves. Now, the question is, there are several questions. One is, why are there waves in the ocean? Well, if you imagine, so first, the thing that generates the waves in the ocean is primarily wind blowing across the surface of the water. Well, you might wonder, if you just have this flat surface of water, you just have wind blowing across it, why does that make kind of waves that kind of go up and down? Why does it not just smoothly blow across the water and, well, maybe not have any effect on the water, but why does it bunch up pieces of water in the way that it does? That's a somewhat, it's an interesting phenomenon, and it relates to all sorts of questions about how gases like air work and how fluids like liquids like water work. So I think a couple of things to say. One thing to say is it's a general feature of fluids like air and water that when they move quickly, they don't move in a smooth way. So if you imagine having water, it's flowing around an obstacle, for example. If the water flows slowly around the obstacle, it just kind of smoothly slides around the obstacle. But if you make it flow more quickly, there's a phenomenon called turbulence that happens, whose origins are not completely well understood. But what happens is, instead of the water kind of smoothly sliding around, it kind of, there's too much momentum in the water. It makes little eddies that form behind the obstacle in a very complicated pattern. And exactly what causes that complicated pattern, well, one can work it out on a computer with taking the equations of fluid dynamics and trying to see how they would correspond, how they would make, what kinds of patterns they would make, and you get some idea that it'll make a complicated pattern. But the full story, I think I've talked about it another time, the full story of how turbulence works is still not particularly well understood. It's something I've studied a bunch of times over the last few decades. There's a bunch of questions about sort of where the randomness in turbulence comes from, and like water or air, any kind of fluid flows rapidly past something, it will tend to produce this complicated, curled up kind of flow. Well, the same thing happens actually right in the air, that you often get turbulence being formed. People, when you're flying in a plane, people will say it might be bumpy because of turbulence. It's actually a rather particular kind of turbulence that causes bumpiness in planes at the altitudes they usually fly at. But it's a general feature of the motion of air in the atmosphere, that it's not just all going smoothly in one direction. I mean, if you say there's a wind, it's a southerly wind or something, wind blowing from the south or something like this, or blowing from the west, whatever it is, you might think there would just be kind of just uniform flow of air from that direction, but it isn't. It blows in gusts, for example. And those gusts are an example of the result of, well, essentially things like turbulence happening in the air. But the main point is that you get, instead of getting sort of just a purely uniform flow of air, you get it in bursts and gusts. You get more complicated patterns of flow in the air. And so when that interacts with the surface of water, that's one thing that makes the water not just be completely flat, because it's being driven by air has these more complicated motions. The other big effect is that once you if you push down some water, it will, you push it down in one place, it will be pushed up in another place. You get waves on water. And when you just sort of, you have some kind of, I don't know, paddle that's hitting the water in one place, hitting it, repeatedly, what will happen is that will push down the water in that place, but then that will cause the water that got pushed down from that place will show up in a different place, and you'll end up getting these waves on the surface of the water. And so anyway, the combination of these things, the waves on the surface of the water being driven by kind of complicated motions of the air in the atmosphere, the end result is that the ocean will end up having sort of complicated structure on the surface of the ocean. It'll have a complicated kind of, it won't just be a nice smooth surface, it'll be something that looks kind of rough. And you see that all the time on the ocean. And once that gets to the point of coming and hitting rocks, it will end up kind of sort of repeatedly bashing the rock in a kind of random way. And that will cause that's what causes the rock to kind of be broken down eventually into sand. And I think what usually happens is that initially a big piece of rock that might have formed is broken into a piece will break off, another piece will break off, and then either the water will keep bashing those pieces of rock, or the pieces of rock will bash against each other, and they'll just get broken down further and further. When rock is formed, there are two basic ways that rock gets formed: igneous rock, which is formed from molten things like lava coming from the ultimately from the liquid core of the earth, and that solidifies into things like granite and so on. And then there's sedimentary rock, which is essentially pieces of sort of mud and sediment and so on that eventually get crushed together to form rock. And sedimentary rock tends to be softer than igneous rock. But both things get, I think, okay, there's a question I don't, yeah, you can get rock, you can get sand from all those kinds of rock. And but in general, sand is formed by the action of water on rock at a shore. So that's and when you see sand, there'll be little particles of sand, and they are little tiny pieces of rock, and they're usually all kinds of different shapes. And the way that sand packs, there's a lot of detail about kind of how well the sand will pack together that depends on things like the exact shape of the little pieces of rock that get formed by the rock being sort of broken apart by the action of water. And then all kinds of other things that happen with sand, like when if you try to make a sand castle or something, having water in the sand makes the little sand pieces of sand stick together better than otherwise, because, oh gosh, well, that's another whole story about how liquids and solids interact, but maybe for another time. Let's see, other questions here. Oh, it's a question from Zayden here. Is grammar invented or discovered? Well, first of all, we have to say, what is grammar? So grammar for human language says what way of arranging words seems like it's correct sentences in that language and what doesn't. So for example, if I say in English, the cat sat on the mat, I've got the cat, that's a noun phrase. Sat is a verb. On the mat is another noun phrase. And I could say the black cat, that would be an adjective qualifying the noun. And so in English, we have various grammatical rules. Like a typical grammatical rule is that we'll go the subject of a sentence, the cat, and then we'll say, well, let me do a sentence that's a little bit simpler. The cat ate the mouse, ate the fish. So then we have the cat as the object of the sentence, ate as a verb, and then the fish is the object of the verb, the thing the cat did. And so in English, the grammatical structure of English is that you form sentences by going subject, verb, object. Other languages do it differently. For example, in Latin, For instance, it's subject, object, verb. The verb comes at the end of the sentence. Let's see. Could I do it in? Can I manage it? Felix is a cat, and let's see. I think I'm not going to be able to retrieve real-time Latin from 50-something years ago. But in any case, in Latin it goes subject, object, verb is the typical word order. But in different human languages, there are different sort of standard constructions for how you put words together into sentences. And for example, if you look at the different languages of the earth, there are maybe 7,000 languages that are sort of still extant and somewhat in use around the world. There's some very big languages and some very tiny languages, but the subject, verb, object, and subject, object, verb are, I think, the most common construction forms for sentences. When people have made artificial languages, like famously the Klingon language made for Star Trek is an object, subject, verb language, if I remember correctly, which is something that doesn't never occur among ordinary human languages, but it's certainly very rare. But so grammar is this way of describing the set of rules that specify how, given a collection of words, you put them together into valid sentences of the language. Okay, so now the question is that invented or discovered? Well, we typical speakers of a language will just know, oh, this is the way that you put these words together. It's something that we all learn at a pretty early age. Usually, it's sort of interesting if you watch kids learn language, they'll typically learn things like nouns first, or just simple sort of one-word kinds of constructs, yes, no, things like that. Chair, this, that, and the other, things that are just single noun constructions, or perhaps other single word constructions. Then later on, one gets people learn grammar, the grammar of the particular language that they're speaking. Now, one of the things that gets tricky is that different languages have different kinds of constructions in their grammars. Like, for example, English has determiners like the and a, the cat, a cat. Some languages don't have those. And for people who've learnt a language which doesn't have those, it's often really difficult to know where do you insert those words, because those words are just not something that one is used to even thinking about as a kind of way of thinking about how the world works. In English, we have some constructions. English is a pretty complicated language, and it has a pretty broad range of constructions across that. There are other languages, for example, English has plurals, cats versus cat. Some languages don't distinguish the singular and the plural. English, for example, doesn't have case endings. It doesn't. Okay, so for a verb, there'll be a verb like I run, present tense. I ran, that's a past tense. I was running, that's an imperfect tense. Run is an intransitive verb, so I can't construct its passive very well. You can't say I was run, so to speak. You could say I was eaten, but you couldn't say I was run. And so anyway, English has a whole collection of different tenses of verbs, and those tenses of verbs are either indicated by additional words like I was running, as well as by markers in the words like changing, like adding things to the end of the word and things like that. So English has various mechanisms for will run, but future tense, it's adding an extra word to make that thing. So other languages will have other ways of indicating, for example, tenses of verbs, like they'll just have markers at the ends of the words. They'll sometimes, I remember in ancient Greek, the perfect tense, I have run is indicated by a reduplication of the first letters of the verb. So all kinds of funky markers that get used in different languages to indicate different tenses. In addition, in English, there are things like we can say, I gave the food to the cat, the cat's food. There are all kinds of different ways in which a cat can enter the sentence, so to speak. And those can be thought of as different cases of the word cat. And for example, when the cat appears as the subject of a sentence, it's nominative case. When it occurs in the object of a sentence, it's accusative case. In English, we don't distinguish those two cases, at least that I can think of. We don't usually distinguish those two cases. We distinguish things like the genitive case with a cat's apostrophe S and so on. And we distinguish things like the dative case by saying things like to the cat with extra words. But again, there are other languages like Latin is a good example where cases are always distinguished by decorating the end of the word. So the whole diversity of different kinds of things that happen in different natural languages about the ways that one indicates kind of the role of words and so on. One of the confusing things is that some of the tenses that exist in English don't exist in other languages. Some of the things I was mentioning, determinants like A and the, articles that don't exist in that exist in English don't exist in other languages and so on. So there are slight differences between the kinds of the inventory of expressive stuff that exists in different languages. Now, in terms of this grammatical structure, I think we all learn the grammatical structure of the languages that we are sort of initially taught. And the question is, for each individual person, they're kind of learning, they're discovering the grammar of the language, the syntax of the language, the way that the words get put together into sentences, because they're hearing lots of examples and they're one's realizing, oh, that's the way it works. I've heard an example like that before. That sounds right, that doesn't sound right. Now, by the way, it's always interesting that kids, when they make mistakes of grammar, usually make mistakes by making the grammar more regular than it is in the actual language. In English, it's absolutely full of weird exceptions where normally you can treat the grammar in a kind of very modular way where you just put together this piece of the sentence, that piece of the sentence, that piece of the sentence. Each one is separate. But in English, there are many, many exceptions where that modularity doesn't quite work. And kids will often, quotes, make mistakes by making the grammar that they say more modular than it actually is in the language as the language is normally spoken. But given that one is trying to sort of learn the grammar of a language which is already being spoken by other people, that's something where you kind of have to discover the grammar. Each individual person has to discover the grammar, and a linguist who's going to visit some obscure place in some obscure jungle somewhere and is recording some language, some local language, and trying to understand it, they will have to discover what the grammar of that language is. Now, in terms of whether we what happened originally when languages were getting formed. So the languages that exist today presumably have, well, it's not completely clear whether they're all derived from a single common ancestor. I mean, we believe that all of us humans are ultimately derived from sort of a single common ancestor. It's not like sort of the human species developed all its features separately 3 times around the world. We know that some other things, like, for example, the idea of writing developed, 3-5 times around the world, apparently quite separately. The idea of language, did it develop in one place? Did it develop in multiple places? We don't know for sure. We don't know whether there was a single precursor language that then split into the 7,000 languages we have today, or whether language was invented separately in different places. I think one general feature of language is the following thing. Language is very linear in the sense you say one word, then you say the next word, then you say the next word, and so on. It's sort of interesting that other things one does aren't necessarily so linear. If you're arranging, stones on the ground, you're arranging them in 2-dimensional array. and that doesn't have that same do this, then this, then this. But the sequentiality of language is sort of an interesting feature, not an obvious feature. It could be the case that if you want to communicate, that you would best be just sort of arranging the stones in some pattern, and that pattern represents the communication. Or you could do what bees seem to do of coming back from their flights and doing these dances that are kind of different kind of well, in that case, patterns in space and time. There are different ways one can imagine communicating, but language is this way of communicating that is very sequentialized, one thing, then the next, then the next. One wonders, and I know there are theories to this effect, that kind of the notion of language as a way to sort of explain things kind of followed the fact that people discovered these sort of procedures for things like making tools, where, again, they have a sequential character to them in the way that people normally do them. You do this, then you do this, then you do this. Kind of a common feature of our experience, that there are many things that are quite sequentialized. Do this, then this, then this. And that's a very basic feature of language. And that's a feature of the kind of the way that we construct grammar, syntax for language, is we're saying these words go together in this sequence. By the way, sort of footnote to this, you can imagine languages that, particularly written languages, that are not in just one dimension, just laid out in sequence, but are arranged in some kind of two-dimensional array. For example, mathematics, when it's written, if you write, I don't know, an integral sign, for example, and you have limits to the integral, there's one at the bottom, there's one at the top, that's no longer a kind of sequential left to right. Most languages are left to right, some languages are right to left, but it's no longer a sequential kind of thing where you're just going from one side to the other. A mathematical notation has a bunch of those things, like a matrix. You'll have an array of things which are just laid out in two dimensions and so on. But human languages mostly are quite sequential. They sometimes, when they're written, they'll have diacritical marks. They'll have various kinds of markings above letters that change them. And some languages have much more elaborate kinds of connections between different letters, and sort of slightly non-local kinds of ways in which letters get joined together, perhaps even not the letters next to each other, but slightly further away in the most obscure cases, most complicated cases that are, by the way, an incredible pain to implement on a computer. But cases which, when people were routinely writing these languages with a pen, calligraphically, were not difficult to think about doing. But I think, so a question that one might ask is, back when language was first being sort of constructed a couple of 100,000 years ago or whenever, maybe longer than that, what did somebody, did cave person Og sit down and say, let's try and figure out how to communicate things, let's construct a language, let's figure out that it has this kind of grammatical structure? My guess is that's not what happened. My guess is that language kind of evolved by it being first kind of what kids do, a noun type thing or a single word type thing. And then sort of people said those two words together, and then that became some kind of little phrase. And then it sort of got more complicated than that. My guess is it sort of organically evolved and got little pieces stuck onto it. And then what tends to happen in language, in the evolution of language, is, for example, common things that were multiple words get smooshed together as a single word. Like, for example, website. Back, 20 years ago, you would always see it written as web space site. But now you'll always see it written basically as website, one word. And that's a common trend in language, that words smoosh together. I know when I write things and I use kind of recently constructed, recently invented kinds of combinations of words, and people who are copy editing stuff I write will say, no, the dictionary says those are two separate words. And I always say, they will smoosh together in a few years. I'm just going to be ahead of the curve and smoosh them together now. But that's, I think, a typical thing that happens, is that language some aspects of language kind of simplify and crush down when they're commonly used. It's a little surprising sometimes that there are sort of turns of phrase that seem very complicated. They don't seem to be, it doesn't seem necessary that it's as complicated as that. And yet they stay in a language, apparently forever. But so my guess is that in the early history of language, that there was sort of constructions were made, and then they were sort of smoothed down by usage. And maybe people, if there was some construct that had extra little pieces in it, that you went, you had a word and then you went blah 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 at the end of the word, and or you went blah 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 to say how many sheep you had or something like that, and that just didn't work very well because people couldn't, really remember very well how many blah blah blahs you'd had. That would be something that would sort of go extinct in the language, and some other mechanism that somebody else had invented would sort of come to life. Now, obviously, in the history of something like English, there are folks like Shakespeare who invented lots of words that make it into the English language, and even I've invented some words that have made it into quite common use, and that's something that happens at a gradual rate. If you were just inventing all new words, then that's a whole different story. And people try to invent artificial languages. Famous example from the 1880s was Esperanto, which was a language which kind of had words that were sort of rough simplifications of common European language words. And so when you look at Esperanto, it's kind of, you can vaguely tell what it might be saying, because you kind of recognize those words as being a little bit like other words that you might know from other languages. But it's kind of a big ask to get people to say, throw out the whole language you know and use this completely new language. Now, I will say that in human language, this idea of inventing languages, I think, is not a thing that is not what historically happened. In the case of programming languages and computational language, it's absolutely what happens. It's much of my life has consisted in trying to build our computational language, Wolfram language, to try and represent things in the world computationally. And that language is a language that is very much invented. And its grammar, the way that one puts together the primitive functions of the language and so on, that grammar is 100% invented. Now, having said it's 100% invented, I know from experience in other things I built, things that people understand, things people don't understand. And the goal in inventing it is to have it be as sort of as natural for people as possible. And so that then has a certain feedback from the things that are just the way that people tend to do things, the way human language works, the way that things seem familiar to people. So in that sense, it's something which is, again, extracted from sort of the ambient experience that people have in the way that they construct language. Now, I have to say, one feature of computational language and programming languages, sort of programming languages are more kind of directly tied into what a machine should do. Computational language I see as being more take the world as it is and try and represent it computationally in a way that also you can feed to a machine, but the original goal is to take the way that humans think about things and to have a sort of precise computational representation of that. But in both cases, the grammar of the language tends to be very kind of very simple and structured. So, and it's defined by a set of grammatical rules. So, for example, let's say you're doing something with, I don't know, plus signs and times signs. So you would say, okay, in the language, you can have blob plus blob, where blob could be some thing which itself has plus signs in it, or has times signs or whatever else. And you're always kind of recursively defining. You say a sentence in the language, call it blob, can be broken down into blob plus blob, blob times blob, and so on. And at each, and then you can reapply that same rule. Blob can be blob times blob. So the blob plus blob could be the first blob there could be some blob something times something. The second blob could also be something times something, and so on. So you have this kind of recursive structure. And when you want to parse the language, when you want to understand what the language is saying, you want to go from that linear sequence, A times B plus C times D, for example, and you want to say, what does that quotes mean? what you do is you make a tree that kind of reverses that definition specification that says, blob goes into blob plus blob. You're going from the plus, and you're saying those are sort of pieces of a tree that eventually that's part of the rule that goes blob goes to blob plus blob. So when you parse a language, what you're doing is you're trying to invert that sort of recursive specification of language. Now, a question is, well, what kind of recursive specifications can you reasonably use in a language? And the answer is that this kind of very structured recursive specification works pretty well. People find it pretty easy to understand that. If you say, well, there are a bunch of exceptions. In this, one feature of that sort of recursive definition is things are context-free, in the sense that if you can have blob could be a blob plus blob, that's true of a blob that occurs anywhere. You're not saying, oh, if that blob happens to occur inside parentheses, then you can no longer do that decomposition. It says it's kind of context-free, it's independent of context. You can have these rules for how you kind of construct things in the grammar, apply independent of context. And in programming languages, computational language, that's typically the way they're constructed. It's the way that's easiest for the programmer to construct them. It also turns out to be the way that's easiest for the users to understand what is a valid piece of syntax and what's not. And whenever, in my experience in doing language design, whenever one deviates from that context-free thing, those are places where people get confused, at least can get confused. Now, one feature I will say in computational language, programming languages, is when I say A times B plus C times D, one of the questions is, if I'm going to make a sort of tree that says what the structure of that is, I have to know the sort of order of operations thing, that times binds tighter than plus. So A times B is one blob, and then the C times D is another blob, and those two blobs are added together by the plus. And that idea of precedence is one of the tricky things in specifying a language, because without that precedence, without knowing that the times binds tighter than the plus, you wouldn't know how to parse that sentence, so to speak. You wouldn't know how to decompose that into sort of this tree-like structure. And one of the things that does get a little tricky is if you have a large number of different operators like plus and times and wedge and slash and all this kind of stuff, it can get quite tricky what the relative precedence of those operators is. Another thing is associativity of operators. If I say A plus B plus C plus D, it doesn't really matter how that groups. It doesn't matter whether you do A plus B first, you do C plus D first. It doesn't matter in which order you do the operations, how you put parentheses in. On the other hand, if you say A minus B minus C, it absolutely does matter, because A minus B minus C, if the B minus C has parentheses around it, there's a different result than if the A minus B has parentheses around it. And usually in subtraction, you usually have left association, in the sense that you group the A minus B first, and then you subtract a C from that. And if you have a minus D, you subtract the D from that. On the other hand, trickier case, if you have A slash B slash C slash D, what exactly does that mean? Does that mean you take the A and you divide by B, or do you divide the B by C, which gives a different result than taking A over B all over C? In which direction does that associate? And I could keep going with more and more bizarre cases. Power is another case. If you do A to the power A wedge B wedge C to represent powers, how do you want that to associate? Or another example, a little bit more programming language specific, is something like A equals B equals C. So what you want to do there, if you left associated that, you would say A equals B. Okay, fine. That means we set A to B, and the result of that is probably going to be B. Well, that's a bit of a whoops, because what you actually want, if you say A equals B equals C, is you probably want everything to be set equal to C. You want B to be set equal to C, and you want A to be set equal to B, which is now set equal to C. And so that's an example where you have to right associate, where you have to put parentheses in on the right-hand side, not the left-hand side. And some of these things are very kind of, everybody's like, oh, well, of course you do that, because they have an immediate understanding of that. And sometimes those things like associativity and precedence are not so obvious to people, and people get confused. Sometimes it's a very painful thing for language designers. You know there are two different choices of precedence, and whichever one you choose, there are going to be cases where people get confused. And it's very frustrating. And in modern times, we're able to kind of patch over that to some extent by using various kinds of user interface effects, kind of hover effects that indicate what grouping is happening, what grouping is implicitly being assumed, so that you can see if you're typing something in, oh, that isn't quite the right grouping, so let me change that before you type it in and just have it be interpreted in the wrong way. But I think in the construction of human language, this idea of context freedom, this idea that the subclauses can be put any way you want, that it doesn't, that, you know, that when you have a subclause that has puts an adjective in front of a noun, that you can do that wherever the noun occurs, and that it isn't just, oh, only in these places where a noun occurs. Human language is also somewhat context free. It has weird exceptions, but it is somewhat context free. Now, human language doesn't tend to allow you in programming languages, in computational language, you can usually kind of go as deep as you want. You know, it's you as a programmer might not understand it very well, but you can go as deep as you want. So, but in human language, we don't tend to do that. I mean, the cat which sat on the mat, which was made of this, which was of this, which did that, blah, 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 blah. And then that whole set of subclauses about the cat, then you say ate the fish. So you've gone very, very deep in the subclauses, and then you come back up and you have a verb, you say ate the fish or whatever. In the, we humans have a hard time keeping track of subclauses that go too deep. Maybe 4 times, 5 times, that kind of depth is the maximum we go to. So there are sort of practical limitations to do with how we can buffer things up in our brains as we try and understand language. But in a first approximation, language is pretty human language is reasonably close to context free and reasonably close to allowing all these different sort of sub pieces to be inserted wherever they can be, so to speak. And you know, I think it's an interesting question whether the you know, that there are, well, human language is sometimes people try and sort of by fiat change like the writing system for a human language. It is much less common that people sort of are at all successful in changing things like grammatical structure of languages. I mean, sometimes people, it's like, you know, newspaper headlines at times have kind of redefined some of the ways that are considered to be appropriate grammar. And I think that's had some effect. Anyway, a few thoughts about that. Interesting question. Let's see. Okay. Several other questions about languages here. Brady says, I believe there exists a 13-letter language from a Pacific island. Do you think a 10-letter language would be useful, since every word would also be a base 10 number? Well, it's an amusing idea. You know, we obviously have 26 letters in English, and there are European languages with a few more letters, a few less letters. This question of sort of how you break the words into letters, this is not every language. I mean, the ideographic languages like Chinese, Japanese, and well, Chinese has pure sort of pictograms to represent typically words or pieces of words. Japanese has multiple different systems, one sort of Chinese character like, and another more alphabetic like English. This question of sort of how many letters do you need? Well, you don't really need that many. I mean, you could construct everything in principle in a sort of binary code. How many is convenient to have? I'm not sure what the right answer to that is. I mean, what one would like to have be the case. Okay, so here's a perhaps a relevant thing. So the question is, when you see a letter E or letter I, does it always sound the same? And the answer is, in English, absolutely not. There are places where the word E, the letter E will be inserted and it says eh, and there are ones where it's E, and there are ones where, I don't know, I don't even know all the cases. There are all sorts of different sounds that that letter can make. Now, there are languages which are, and so that means, for example, that spelling is difficult in English. That because you can't just say, what sound does the word make? Okay, I know the sound, the V sound is always a V. So I just have to put a V there when I spell the word. Well, actually, PH could make a V sound in some words, et cetera, et cetera, et cetera. So you don't know, there isn't a unique correspondence between the sound of the word and the letter in the word. And that's a feature of English. And of course, English had some real horrors in its spelling in the past, because there were times when people said, let's make the spelling sort of record things about the meaning of the word. I think a famous example is the word debt, which at times in the past was just spelled D-E-T-T, for example. But somebody had the bright idea, let's burn into the spelling of the word something that means something about the meaning of the word. And since in Latin, the word for debt, debt is a debitor with a B, somebody had the bright idea, let's put into the spelling of the word debt in English a B. Now, obviously, people weren't saying that B, so it just became this weird extra piece that was put into the spelling of the word, and that in order to know how to spell the word from it being spoken, you just have to know that fact. So in any case, one thing that can happen is languages, I believe Russian is an example of this, as a language which is essentially phonetic. That is, if you know how to say the word, you know how to spell the word. Not true in English. That's why we can have spelling bees in English, because a spelling bee will be rather trivial in a language where all you have to do is hear the word said, and you can then write down the spelling of the word. And you don't have to know anything about the history of the word and the sort of origins of the word and all those other kinds of things that contribute to English spelling. But so I would think that there's a sort of by the time you've got a language with a set of complicated sounds in it. So when you have a word, there is its spelling as in written language. There's also its phonetic version as a sequence of phonemes. So we have in English, how many is it? 30, 40 phonemes? I'm not sure. There's different kinds of sound fragments from which our words are made. And those sound fragments aren't necessarily single letters. They may be combinations of letters. They may even, in some cases, perhaps, I'm not sure, I don't immediately have an example of this. Well, okay, there are weird examples. The word naive maybe does that, where you have, maybe not, where you have a single letter that can actually be broken into multiple phonemes. But anyway, there's a phonetic version of the word, which is phoneme number this, phoneme that, and there is a notation for phonemes, the IPA, the International Phonetic Alphabet, that has sort of somewhat based on the English alphabet, but it has, backwards E's, and it has all kinds of other letters that represent kind of the sounds that get made in different languages. And the full inventory, I don't know, maybe 100 or so sounds that we humans get to make with our vocal tract. And sometimes there are kind of funky sounds like clicks and whistles and things like this, which are sort of part of the phonetic inventory of things that can be used in languages. So I would kind of think that there is a certain pressure to have more letters in a language, because then it becomes more phonetic. I mean, given that you're using multiple sounds, and since we can make those sounds with our vocal tracts, why not use them? If we can make them, why not have sort of one letter per sound? Might be a more kind of rational way to set these things up. Now, obviously, people hadn't that kind of construction, the idea of let's construct the language, that didn't really happen that way. And I think, the way that letters were presumably there were actual inventions of letters, and there were actual people who figured out, we want this letter, we want that letter. Probably somebody invented the letter W, for example. And I bet it's not known who that was. But in these kinds of things, that's a those things have to get invented. And I think probably when typewriters and printing came in, there was that forced a certain amount of standardization, because like if you have a typewriter, you have a certain set of keys on the typewriter. Printing, you have a certain set of font characters that you've made. And so you don't want something where, oh, well, just every so often people have this weird extra letter. Like in English, the word naive, for example, if when you see it written in very literary kind of places or magazines and so on, the I will have a double dot on top of it that represents it's a differently sort of said I. But that kind of sort of pedantic writing of something like that, most of the time you're just going to blow that away, because it's like, I don't have an I with two dots on it on my keyboard, I'm just going to type an ordinary I, and pretty soon all that stuff goes away. I think it's something which sort of was interesting in the early days of things like texting and so on, when a lot of languages, a lot of the kind of elaborate markings that exist and extra letters that exist in some languages weren't there in texting. And I think for a while it looked like some of those kinds of spelling and so on would go extinct in some languages. But as the technology caught up, they came back, and I don't think they've gone extinct in that way. But when it comes to the writing of languages, the number of writing was independently invented maybe 5 times or so. And then the question is, if you've got a language that was basically a spoken language, how does it get to be a written language in the first place? And the answer is somebody, in some cases, in more modern times, somebody just invents a way of writing the language down. I mean, famously, there was a monk named Cyril, I think, who did the Cyrillic alphabet that gets used, in Russian-speaking kinds of places. And I think the Armenian alphabet, there's a definite person that invented that, and so on. And we don't know the person who invented the sort of Phoenician alphabet that turned into our English alphabet. But when it comes to sort of some sort of indigenous people somewhere who didn't have a written language, or at least none that anybody identifies as a written language, then somebody went in there, some anthropologist, some linguist went in there, and they said, well, I'm hearing these sounds, let me write down, let me construct a written language for this particular place. And that's how almost all of the 7,000 languages of the earth, a largish fraction of those that were just spoken languages, and somebody just had to invent the way of writing them down. And sometimes that was done better and sometimes it was done worse. But one shouldn't, I think, deduce too much from the way that these things are written about sort of intrinsic features of those languages, because that was really an add-on. It tells you more about the education of the linguists, perhaps, than it does about the actual language itself. Let's see. Oh boy. Let's see. Okay, so RBS is asking, can a natural programming language replace concrete programming languages? Well, so one question is, why can't we just talk to our computers and tell them what to do? And, I've been deeply involved in this issue and in, constructing Wolfram Alpha, which is a natural language interface system, and in constructing the kind of tools for intelligent assistance, where you just use whatever comes into your head, whatever you think to type. So the basic experience that we have is for short utterances, for a short question, for a short thing you want to describe, natural language works quite well. when you have a bigger, longer structured thing, it's like you're building a tower. And if you just sort of throw pieces of wood together at the beginning, you're not going to be able to build a very tall tower. In order to build a tall tower, you have to kind of arrange things in a nice structured way. And in sort of a computational language that is a structured language, you can absolutely build that tower taller and taller, and you can make a program that's 1 line, 2 lines, 5 lines, 10, 100, 1,000, 1,000,000 lines long, and it's still going to be something that sort of hangs together coherently and is useful. Whereas if you try and do that all with natural language, it's something where you won't be able to systematically keep building up that tower. It'll be something where it's like you keep on having to go back and say, what do I actually mean by that foundational concept there? And it gets difficult to do. Now, I think that one of the things we found is that, as I say, it's really powerful to mix kind of structured computational language together with little fragments of natural language. So, for example, in Wolfram language, it's pretty common if you want to say, what's the distance? Well, what's the, I don't know, make a map that shows the path around, I don't know, European capital cities with, I don't know what, with indicating each city by the flag of the country or something. Okay, that was a reasonably easy thing for me to describe, but the thing that is sort of realistically and reliably sort of parsable is something like countries in Europe. That's something where one can realistically interpret that as kind of just one interpretation of that. Well, you can ask, oh, I don't know, is Turkey in Europe? Is Russia in Europe? Those kinds of things. There are details of meaning, but in terms of the what is the basic structure there, that's a thing that's fairly easy to describe. And so that little fragment is fairly easy to deal with. But then, and so what we find is, you know, in Wolfram language, it's just control equals, and you type some natural language, and then you resolve that. It turns into some precise thing that you can see what it turns into, and then you go on and you build up your more structured thing on top of that resolved what the natural language meant piece. And I think that's a pretty good way to do things. Now we have this product called Wolfram Alpha Notebook Edition, where Wolfram Alpha is a system where all you have is natural language. You're just asking questions purely in natural language. Wolfram Alpha Notebook Edition is kind of a hybrid situation where you are sort of asking small questions in natural language. They're interpreted into our symbolic language. Then the result of the question is generated. Then you can keep going and you can build up this whole sort of notebook of computations. And that's kind of the compromise case between the purely structured language and the pure natural language case. And it seems to be really quite nice and quite very useful for certain kinds of things, particularly useful in all sorts of educational settings, data science settings, things like that, where you're kind of just each individual step is something comparatively easy to describe. But as you build these steps up, you get something more sophisticated. And in the sort of mechanism by which this works, every step you build up, you're kind of confirming that step. Oh, yes, that's really what I meant. And then you build the whole thing up, and it makes something good there. Let's see, all kinds of questions about quantum mechanics and things. Well, let's see. I think we don't have time for more than maybe one or two more. Well, okay. There's a question from Arslan about thoughts on languages from the perspective of category theory. Seems like category theory encompasses all of math. Okay, let's see if I can give you an elementary version of what category theory is. So in math, there are different kinds of math one does. One does arithmetic, deals with numbers. You know, it has operations like addition and etc. But the things one's dealing with, they're numbers, 2, 3, 4, whatever else. There's also algebra, where you have things like x's and y's, and you have operations that say factor a polynomial or something like this. That's a different kind of area of math. Or you might have geometry, where you have kind of triangles and squares and angles and things being congruent to each other and things like that. Each of these areas of mathematics has kind of a way of, it has certain constructs in it which have certain relations to each other. So, for example, you might have something where you say, oh, I can transform every, oh, I don't know, what's a good example? I can take every collection of numbers I have and just say how many numbers are there in that collection. That's sort of a transformation from any collection of numbers to just the size of that collection, something like that. But in any case, we can think of these areas of mathematics as, for example, let's say in arithmetic, we might have operations, we might have numbers, we might have, I don't know, maybe take algebra. We might have things like rational expressions, something over something. We might have polynomials, we might have individual variables, things like this. We have all these different kinds of things. Well, I never tried explaining this at an elementary level before, so please, and this is not category theory is one of these things that's in kind of the higher reaches of abstract mathematics, and it's but let me keep going here. So basically, the idea is you have these different kinds of things, these different kinds of objects in, let's say, algebra or something, and then you can kind of think of what is the structure of algebra. Oh, it's a way of relating one set of objects to another set of objects. In category theory, that kind of relation is called a morphism. And it's kind of, it tells you this set of objects is sort of related to this set of objects, which then can be related to another set of objects and so on. And so category theory tends to have these chains of relations. You know, something F is something, some objects X are related by a morphism F to objects Y, which are related by a morphism G to object Z, and so on. And you get these kind of chains of relations like that. One of the things, so when you have those chains of relations, when you think about them in terms of computation, you'd say, well, okay, I take the original set of objects and then I apply some computational operation, some function to those, some computational function to that original set of objects. Get another set of objects, I apply something again, I get another set of objects. So I've done one computation, then I've done another computation. Okay, so in general, when you do one computation, then another computation, there's absolutely no guarantee that there's an easy computation that does the equivalent of both of those together. In fact, in many kinds of computations, there's this phenomenon that I kind of developed called computational irreducibility that basically says that in general, you can't crush things down. If you've got one piece of a computation, then another, then another, then another, there's no fast way to figure out the end result. You have to just go through all the steps and see what happens. But category theory has an assumption. It says, well, actually, whenever you can go operation F, then operation G, there's another operation, let's call it Q or something, which is the one-step operation that does F and G together. And you don't really distinguish the sort of the Q operation, the super operation, from the do two operations together. There's a big assumption in category theory. It's a big kind of structural foundation. It's a thing called compositionality in category theory, is that essentially assumption that that always works. We know that in general computation, it doesn't work. So category theory is a kind of an idealization of general computation that says we're looking only at those computations where there is this kind of jumping ahead possibility. And so when we try and use category theory to kind of represent what's going on in math, whenever what's going on in math has this computational irreducibility phenomenon, it isn't a very good fit for category theory. Category theory is putting this sort of overlay on top of what's happening in math that is kind of a simplification that may be good for us understanding what's going on. So it's similar, you know, when you think about, I don't know, gas molecules bouncing around in a room, they do very complicated things. But when we say, let's let's look from a distance, let's aggregate all of that and just look at the overall pressure of the gas. And then we have a simple gas law. Something similar is happening with category theory. There's sort of underlying computational stuff that's going on, but you're only looking at this sort of aggregated piece that's sort of from a distance and that has these simplifying properties that make it easier for us to actually understand what's going on in math. Now, okay, having said all of that, there are ways, okay, so that's sort of the category theory shtick. It's kind of this superstructure that you can put on top of math that kind of explains structurally what's happening in different areas of math. And with this simplifying assumption that helps one understand these things. And one of the important things about category theory is because even though the objects one's dealing with in, let's say, arithmetic, geometry, whatever, are very different, category theory provides this kind of structural overlay that lets one translate kind of what's going on in one area to what's going on in another area. You know, it'll be a long story, but a big project that I did earlier this year about metamathematics has to do with understanding this kind of the structure of metamathematical space, the structure of the space of sort of all possible mathematical constructs. And this kind of idea that category theory is the kind of continuum limit, is the kind of large scale feature of, it's one of the ways to describe on a large scale what happens in kind of metamathematical space. Seems like a useful kind of way to think about things. But I think that there are other aspects of kind of the possibility of doing mathematics that sort of emerges at a large scale. Okay, how does this relate to language? And I have to remember how this all works. There was a chap called Jukowitz back in the 1930s who, long before current ideas about the construction of language, due to people like Chomsky and the phrase structure grammars and all of this kind of tree structuring of grammars and things that was only really codified in around 1956. There was a much earlier approach to language that was made that is a more, that sort of turns into category theory. Okay, how does it work? Here's how it basically works. The normal way of thinking about language is you say, I'm going to take a sentence, I'm going to break it down. It's got a noun phrase, a verb phrase, a noun phrase. Let's say the noun phrase breaks down into an article, a determiner, an adjective, a noun, and so on. And that's kind of a break things down in this kind of tree-like way. And that's how when you diagram a sentence, you're typically showing this tree-like structure that sentences have. Okay, so a different idea is imagine that words kind of multiply together. So when you say black cat, it's kind of like having black times cat. It's kind of like having a mathematical expression where there is a, where you're kind of combining words sort of like you combine elements in a multiplication or something like this. So there's a different way of thinking about how you construct grammars, that is the so-called categorical grammars, that are much more along the lines of you apply functions to words. So in ordinary grammar, the ordinary kind of way of doing it with sort of tree-like grammars, you're sort of breaking down the sentence in the way I described. But an alternative would be to say, let's take the cat construct and let's sort of multiply in, let's apply the blackness function to it. And so we have kind of black cat is not quite a multiplication, it's really a function application. To cat, we apply the function black. And then we say, you know, sat on the mat, we apply the function sat to this, and then we apply that function sat has two arguments. It has, you know, the cat and, well, oh gosh, I should have had a transitive verb, but on the mat is the other part of it. And and so the way that categorical grammars work is this idea of kind of applying functions to get to construct your sentence. So your sentence becomes a bunch of function applications. and it's also deeply related to combinators. Now, what can you do with this? Well, okay, so these function applications are like these morphisms I've described in category theory. And okay, among the things that happen are, okay, so in category theory, you'll have these objects transformed by morphisms to other objects and so on. You have these chains of things. You also have these things called functors, which are things that sort of map from one chain to another chain. So one chain might be in arithmetic, and there might be a functor that maps that to a sort of corresponding chain in algebra. Well, so in sentences, the analog of a functor would be something that maps one sentence defined by this function thingy, which is like morphisms. You map that into another sentence. So that's kind of an interesting thing, because one of the things I was curious about a lot when we were first building Wolfram Alpha is what I call meaning to meaning, sort of sentence to sentence transformations, meaning to meaning transformations, where you would take one sentence and you would say, I've got this sentence, the cat sat on the mat, let's say, or the black cat crossed the road. And you ask the question, how many different ways can I say that sentence? Actually, that's a really bad example. Example that we used to use as a test case for people working on linguistic curation for Wolfram Alpha was how many ways can you give change for 35 cents? So sort of in that case, there are things that are a little bit like how many ways can you make 35 cents out of coins? What what combination of coins, how many different combinations of coins make 35 cents? Those kinds of things. There are many different ways to say essentially the same thing. And that is okay, I think that's actually I've got to go. And today is a company holiday day, so I have slightly different constraints. In any case, what I was just to finish this one thought, so this notion of categorical grammars is this notion of grammars in which you're constructing things by applying functions, and then there are these things like transforming one version of a sentence to another version of a sentence which has the same meaning. And one of the things people wonder about is whether by thinking about grammar in terms of the application of functions, you can more immediately have something that represents the meaning of the sentences. It doesn't come for free. That's a separate whole issue of designing a computational language, the thing I just spent the last 40 years doing, that has a way of representing meaning by applying functions. That's not something that you magically get by taking natural language as it exists and sort of parsing it in this way, whether you use categorical grammars or any other kind of grammar. That's not the point. The point of attaching, of kind of representing meaning in a computational way is a whole separate set of issues. So in any case, that's a bit of a story. I'm actually pretty amazed that I managed to do, well, I don't know how well I did here, but category theory is a pretty abstruse area. And I at least made an attempt to explain how it works. And categorical grammars are even more abstruse. I noticed Triv asks, what limitations does Wolfram Alpha currently have, and what methods are you exploring to address those limitations? That's a long story, but the one thing that is very unforgiving about operating a system like Wolfram Alpha is every day we have a whole boatload of what we call fall-throughs. That is, questions people ask that we couldn't answer. And so that's a very good, we do a pretty good job. If we think we can answer the question, we actually can answer it. We're not sort of guessing, oh, statistically, we might be able to give the right answer. If we think we know the answer, we think we got the right interpretation of the input language, and we think we actually computed the right answer. But we're pretty confident of that. But nevertheless, we can see every day a set of questions that get asked that we couldn't answer, And that is kind of the giant to-do list, so to speak, that we have for the last, well, since 2009, when Wolfram Alpha launched. We've been steadily grinding through all of the different kinds of fall-throughs that happen to make Wolfram Alpha understand and be able to compute as much as possible. All right, I should wrap up there. Well, thanks for joining me, and thanks for those questions. And I see a lot of other interesting questions here, and hopefully I'll get to address those another time. All right, bye for now.